without further ado, we want to, very happy for Aaron to be here. And yeah, we'll be very interested in this talk.
Thank you. Yeah, thanks for the nice introduction and thanks for having me. So I'm going to talk about OpenEuroLLM today, which is a European initiative to train a family of large language models for European languages. Oh, sorry. And so, yeah, if you look at the current landscape of large language models, you will see it's mostly dominated by models from China or the US. Most notably here, there's the frontier models, and the only maybe exception here is Mistral. And I don't want to go too deep into the geopolitical aspects of this here, but it certainly has some consequences on the science that we do here in Europe, and in particularly our ability to use this model for research, which is often limited. So, for example, if you look at LLaMA 4, it's right now restricted in Europe, so make it very hard for as European scientists to build on it and experiment with the latest achievements in this direction. And if you talk about large language models, we can essentially differentiate between three different classes of models. So in the one class, there are closed models or frontier models, such as GPT or Anthropic Claude, where we don't know how those models actually look like. We don't know which data they were trained on. We don't know how they were trained on. They're a total black box. Um, However, they are used right now, the frontiers, so they're right now the most powerful models. On the other hand, they're the open weight models where we have access to the model weights, so to checkpoints, but we don't know which data they were trained on, and we also don't know how they were trained on this data. And so here, popular examples are Qwen or LLaMA. And those models tend to be somewhat maybe smaller and trained on less compute than the frontier models, but they're closely catching up to those models, especially with the latest generation from the Chinese models like Qwen or Kimi. And then the last class, which is also the class that we're focused on, are fully open models, like open source models, where not just the weights are publicly available, but also the data set, the training procedure, and yeah, post-training, and so on. And those models tend to be even smaller than the open weight models. And here popular examples are Olmo from the US or Bloom, which was also trained partly in Europe. Now, I would argue that actually, even those open source models tend to be not quite as performative as the open weight models, we still need more of them. There are obvious reasons like transparency, right? We want to independently verify and audit those models, but also reproducibility, which is important for science. On top, we also they have a strong advantage that since those models tend to be smaller, that they also come with less inference costs. So it's much easier to deploy those models in an academic setting or in a small or medium enterprise. Last point, which gets increasingly more important, is compliance, right? So those models should comply to current regulations, such as in Europe, for example, the European AI Safety Act. Now that brings me to OpenEuroLLM. As I mentioned, OpenEuroLLM is a 3-year project funded by the European Union to train a family of large language models that is particularly focused on European languages. And that includes almost 40 different languages, such as official European languages, German, English, French, and so on, but also co-official or commercially interested languages. So those are also a lot of languages, involves or includes also a lot of languages where we don't have much data, such as Bulgarian, Albanian, and so on. The project includes 20 different European institutions. There's universities, startups, companies, and so on. So, for example, Tübingen is the Alice Institute where I'm working on, but also the Tübingen AI Center. Now, what's the scope of OpenEuroLLM? So I already mentioned it's focused on multilingual European languages, but it also includes things like programming languages, math, as well as instruction following or reasoning, here also in the multilingual context. And as we're going to see later, it's not just dense models. We also explore other architectures like sparse models. Whereas if you could look at the current landscape in Europe, or actually all of the European language models, like Apertus and so on, they're all vanilla dense models. What's not part of OpenEuroLLM is fine-tuning to specific use cases. However, there's another project also funded by the European Union called LLM for EU, And they want to use our models and then fine-tune them to specific domains like finance or science and so on. Also, OpenEuroLLM is exclusively focused on text. Also here, there's another European project that's also where also Tübingen is heavily involved in. It's called Elliot, that aims to train multimodal models like for audio, images, and so on. Now, OpenEuroLLM is organized essentially in three different technical work packages. The first work package is the generation of the data. Work package, then the second work package is the LLM building, so that includes pre-training and post-training. And the third one is evaluation in a multilingual context. And here the Alice Institute is mostly focused on work package for LLM building and evaluation. And while the first question that people are going to ask if you talk about such a project is like, okay, what about the compute, right? So what are the compute resources you have and which compute infrastructure are you going to train on? And here we use UHPC, which is a joint initiative from the European Union and certain European countries to pool supercomputer resources in Europe together. Also, here 5 UHPC centers like Barcelona, Italy, Finland, and Germany are also part of the OpenEuroLLM. And UHPC oversees all the pre-exascale and exascale machines. So one of them is Jupiter, which is now the first exascale supercomputer in Europe. It was supposed to go online last year in October, but they're facing some technical issues. That's why they're probably going to start in summer. We already have access to the machine flow, not to the entire machine, but enough to get us to do let us do some experimentation here. And it's, well, as I say, exascale supercomputer, and according to this list here, it's the 4th largest supercomputer in the world. What does it mean? Just to give you some ballpark, it has like 6,000 nodes, where each node has 4 H100 GPUs, which corresponds to like 24,000 GPUs. So it's a very large machine. And we have access to it through various compute grants, not just Jupyter, also other machines like Leonardo or Lumi. And what I'm particularly excited about is that we also got last year the strategic compute access or the strategic relevant status, which give us essentially access to 5% of each of those supercomputers. So it amounts to roughly 10 million GPU hours. So in total, as of today, we have like around 20 million GPU hours, which is like millions of euros worth of compute, right? However, with large compute, there comes large responsibility because we want to use this compute most efficiently, right? So, which means we need to make sure that if we scale our training process and parallelize it with more GPU nodes, we also increase our processing rate, right? And ideally, this would be if you double the number of GPUs, we double the throughput. This is in practice rarely the case, especially if you go to here, like for example, 1,000 GPUs, because then you face some bottlenecks or synchronization overhead or data loading issues. But here, there's a lot of work that we spent into optimizing our training procedure that we get as close as possible here to the optimal scaling. There's a lot of technical hurdles that we need to face here. Now, let me quickly talk about the actual training of the models. Here, as you probably know, there's pre-training and post-training. And in pre-training, there you face a couple of challenges. And if you train those large-scale models, the first obvious thing is which data do you want to train on. And this is particularly interesting in a multilingual setting. But there also are other things, what you talked about, throughput optimization, right? You want to make sure that you most efficiently train across those thousands of GPU nodes. But also scaling the training procedure, right? This is required to essentially make an informed decision which model you in the end of the day want to train. Then another very important point, which is always somewhat ignored or neglected in practice, is evaluation, right? So you want to be very careful with measuring the quality of your model if you scale it up. And as I mentioned, in a multilingual setting, selecting the data is actually not quite trivial because there's a thing called coercive multilinguality. Most of our benchmarks that we use in open source benchmarks everybody uses, they're mostly dominated or English dominated. Now, if you reduce the portion of English in your pre-training data set, the performance goes down. Because it's in the left part here, right? You reduce incrementally the amount of English and increase the amount of other languages, then the performance goes down on those English benchmarks. But on the other hand, the performance on those multilingual benchmarks obviously increases. But seems to be some sort of a sweet spot, right? And finding the sweet spot is essential to achieve a good performance, not only on those English benchmarks, but also on those multilingual benchmarks. And on top, as I mentioned, a lot of the languages that we include are so-called low resource languages where not a lot of data is available. So think of it, for example, Albanian or Bulgarian. The question is, how do we get more data for pre-training on those languages? And something we tried out, which performed actually surprisingly well, is to synthetically generate this data by translating high-quality English data. And it turns out that this often tend to work better than training on native data, because this native data is often not a high quality. Now, once you figured out the data set, make sure the next question is obviously which model you want to train in the end, right? And since it's super expensive, you can't train multiple models on a full scale. So what we need to do is we need to train a lot of models on a smaller scale and then try to extrapolate to the larger scale, right? This is the idea of scaling laws, essentially. And this is maybe how it looks like. This is with experiments run by Nicolo, where we train essentially a lot of hyperparameter configuration. So each cell here is essentially one hyperparameter configuration on different parameter counts. Those are the rows, and different token budgets. Those are the columns. And then based on this data, essentially we can extrapolate, okay, how well would our model perform if we increase the compute, essentially. And here it's important that we not just look at validation loss, which is typically done, but also on downstream loss, right? So we take all the checkpoints and validate them on downstream tasks and make sure that the model also that the trend, how the trend looks. So here you can see this is our model here, so it's to the left, and it scales actually quite nicely here across flops. And compared to other models, it's tend to be much more efficient, right? So we achieve the same performance orders of magnitude with orders of magnitude less compute than other models like small-m2 or ULM, which is a predecessor or a previous project that tried to train the multilingual European model. Those results that I showed you were mostly done on monolingual English, and we're now extending that to multilingual data sets. But there are also some further research questions that we need to address. So especially if you want to model here the performance, we found out that the models in the literature are not perfectly matching the data that we observe, right? There's like discrepancy between the model fit and our data. So we need to improve essentially those models to predict learning rate and batch size on larger scales. Now, I already mentioned, so we not just want to train vanilla dense models, but also want to look at more state-of-the-art architecture. And one of them is a mixture of experts. They became quite popular, especially with the latest generation of those Chinese models. And the nice thing here is you can increase the parameter count without increasing the compute that you spend per token, right? So make your model essentially much more powerful without increasing the compute it takes to train this model or to do inference of this model, actually. And we did some preliminary experiments here by Sagatan and Mabash, where on a fixed scale, we compared our dense models with our MOE models and achieved quite a interesting or promising gain in downstream evaluation. Again, this is on a fixed scale, so and in order to make sure this holds for larger scales, we need to run this also on multiple scales and see that the trend essentially stays the same compared to the dense models. Now, I'm running a bit out of time, so I want to quickly talk about post-training. In post-training, you also face similar issues, right? You also need to make which data set you want to train for use for instruction following or reasoning. But also evaluation here becomes much more important, but also much more complicated, right? Because you now need to test essentially the text generation or the instruction following capabilities of your model across different languages. And on top, with post-training, it's a lot less clear how to select those hyperparameters. So there's nice scaling behavior that I showed in the previous plot that we've seen with pre-training, don't necessarily translate to post-training, and there it's a bit more messy. And we don't know exactly how hyperparameters change, for example, if you increase the model size. Now, I want to quickly show you some preliminary results that we have on our current reference model. So this is not like our flagship model that we're going to release. This is more like an experimental artifact. But as you're going to see, it's very interesting or very promising performance. And here, it's a 9 billion parameter model trained for 4 trillion tokens. And we use a 60-40 split. So 60% is English, code and math, and 40% is multilingual data. And for the post-training, we use OMO free pipeline, which essentially is right now the state of the art for open source models. And here you can see the comparison of our model, this gray line, compared to OMO free, which is the state of the art open source model, and Apertus, which is essentially our competitor from Switzerland. And well, OMO free is more focused in English, but Apertus also is focused on multilingual data. So it's more, in that sense, the more closer competitor to us. And our model has been only trained for 4 trillion tokens, so it's substantially less than Apertus or OMO, but performance is quite close. So OMO is still better in English, but compared to Apertus, it's not a significant gap. But what's maybe more interesting is that, and this is the same in German, and here the gap, we essentially match the performance of Apertus, but with just less than a third of the compute. You can see also the comparison again with OMO, as I already mentioned. So on the left-hand side, you can see the performance English, and here we don't match OMO, but on the other languages, we are quite a bit better or match the performance of OMO. And even for it has been trained for a lot more compute than our model. So those are quite promising results. But now for the first actual model release, we want to train similar sized model, but from a larger token budget. And that's probably going to start next month if everything goes well. And then later in the end of this year, we hopefully going to start training the first flagship model, which will be something like a 32 billion parameter model. And yeah, with that, well, I want to first thank the entire consortium. This is a picture from the first kickoff meeting. But particular thank you to our team here at the Alice Institute in Tübingen. And yeah, here's some additional links if you want to know more. And yeah, with that, thank you and happy to take any questions.